I'll be starting the last lecture of linearity and dependent types today. And so in the last three lectures, you've seen, what linear types are as a calculus and how you can use them to support things like imperative programming. And once you make these kinds of applied extensions, how you might go about proving the soundness of the extension. And well, I guess sort of the sketch of how to do it. And what I'm going to talk about today is finally put the dependent types into the linearity and dependent types. And this is going to be some work that I did with a fellow named Pierre Prodek 2 years ago. And one of the lessons of this work is not technical, and it's simply that you should when you start doing research, don't be afraid to take on ambitious problems, because just because someone famous hasn't solved it doesn't mean that you can't do it. Because Pierre came to me to do a summer internship, and I thought, okay, maybe this will be something to look at. Maybe we'll make some progress over the summer. And within 2 weeks, he had done most of the work, and I was left scrambling for what to do for the rest of the summer. And so in a lot of ways, a fresh perspective is just as important as long experience in the field, and sometimes even better than that. So basically, don't be afraid of taking on big problems, because it might just be that you just need a fresh perspective and a new idea. So to recap what we've done so far. So what I talked about on Monday was about the adjoint logic presentation of dependent type systems. So what we did was we said, okay, we'll have two universes of types. So we'll have our functional types, our intuitionistic types. And we'll have our linear types. These will live in separate universes or categories, or however you want to think about it, and we'll connect these two type systems by means of a pair of modal operators. And so we have a modal operator embedding linear types within the intuitionistic world, and we'll have an operator allowing you to manipulate intuitionistic values linearly. And these two will form in the semantics and junction, and you get a beautiful equational theory out of it. So that's all great. And then we talked a bit about how you can use a linear type system to control the usage of state, and reason about things like pointers with explicit allocation and deallocation, and even type changing updates to them. And what we did was we said, okay, we'll do this by adding a type of pointers to the intuitionistic world. And then what we'll do is in the linear fragment, what we'll do is we'll add a capability type denoting the permission to access a particular region of memory that has some particular contents in it. And what we had to do though was, because the pointer and the permission to access it were separate, we needed some means of identifying which pointer corresponds to which capability. So we said, we'll introduce this category of names, of pointer names. And this way, if I have a pointer and I have a capability, I'll be able to tell whether this is the right capability for this pointer or not. Because if we didn't have it, we might have a type of pointers and a type of capabilities. And if you have a pointer and a capability, you might not know, okay, does this pointer actually point to this region of memory or not? And because we didn't know that, in order to establish this connection, we introduced a yet another syntactic category of names, and we had to augment our judgments with this thing right here, which would be the set of names that are currently in scope, like region names or location names. And I mean, this works perfectly well, but it's honestly a little bit unsatisfying because we had a calculus that has like an extremely nice proof theoretic and semantic interpretation, and then on top of that we have a we have this application in mind, and rather than simply extending our calculus with some new constants for the new types, we had to like go through and do some fairly dramatic surgery to the calculus. We had to carry around an entirely new context just to bear the names. And okay, it works, but it's not like super great. And if you remember Edwin's talks, there seems to be a really nice alternative to this, which is to simply use dependent types. Because what we can imagine doing is we say, well, we have this pointer, this term representing a pointer, and we have a capability, and what we want to do, it seems like a perfectly sensible thing to do, is just to say, let's make that linear type dependent on the particular pointer. Okay, so now this says, here's a capability. The pointer here holds a value of type X. And if we could do that, then like this whole business with a extra context of names, which are sort of the static analog of the pointers, which are the dynamic thing, that all just goes away. And you can just say what you mean. Because when you're thinking about your program, you don't think, oh, well, I have this pointer, but I'm going to think about like a static representative of it. You just think, okay, what memory does this pointer actually point to? And so that sounds like a great idea, but when you start thinking about combining dependent types and linear types, this is an idea that is immediately appealing, and many people have tried. And pretty much everyone has foundered on some issues which are just sort of fundamentally stupid. So the variable rule for linear types is set up so that it constrains the usage of your variables. And so we have a rule that says, the variable rule says the following. It says, and this is the hypothesis rule for linear logic, and it says, if I have exactly one linear hypothesis A, I can conclude A. And here are the intuitionistic hypotheses off to the side. So to make this even sharper, let's forget about it for a moment. And so it says, I have a linear hypothesis A, and I will conclude that I have an A. Okay, so that's the identity principle. Everything is great. And in the simply typed case, everything is fantastic. There's only one problem, and we can even write down let's even do the function type. So the structural rules of the lambda calculus are going to ensure that every variable is used exactly once. So we'll say delta will tell us lambda a dot t has the type a lollipop b. And let's do the application rule too, so that I can put the context splitting on the board as well. Okay. Okay. So this says I can type a linear function if I assume I use the binder once. So I assume I have an A of type A and prove that the body has the type B. And then when I do an application, I want to ensure that every variable gets used exactly once. So I'll split up the context into two parts, one for the function and one for its argument. And then up here, the hypothesis rule demands that the context have exactly one hypothesis in it, and then everything plays together to ensure that each variable is used exactly one time. So we saw that on Monday, and that works really well. The trouble is that in a linear type system, how do we count usages? So let me write down what the function typing rule in a linear type in a dependent type system looks like. And so what this says is lambda x dot e has this let me use x's and y's, so my notation is consistent. So we'll say to type a lambda, we'll assume that the argument has the type x as before, and that the body has the type y. And I'm writing pi x dot y because I'm saying that this variable x can occur inside of y. So Edwin in Idris writes this as x colon x arrow y. And you can think of this as a kind of universal quantifier. So we're saying for every x of type x, I can build you a y of x. So you might even write it like y of x, so that you can see that the x is permitted to occur inside of the definition of y. Okay, so that's fine. And now let's look at the application rule. So we'll say, okay, if I have a function of pi type, and I have which says e is a function and its type is for all x of type x, I get a y, and I have an argument of type x, then the application is well typed. And at a high level, the linear typing rule, the linear application rule, and the application rule for dependent functions look pretty similar. In both cases, we say if the head has a function type and the argument has the argument type, then doing the application gives you something well typed. And so here we're saying if t has the type A lolly b and t prime has the type A, then the body has the type B. The application has the type B. And here we're saying if E has the type for all x of type x dot y and E prime is an x, then we say that the application has the type y with E prime substituted for x. And one's first thought is, oh, okay, we'll just copy this and everything will work great. So you might say, well, let's see what we can do. Let's see, if we had a sort of dependent function type, what would happen? And we'll say, okay, well, we have a t of type dependent a lolly b and a t prime of type a, and the application, oh, wait a second. Now we're running into some strange issues here. So issue number one is, does this usage of x count as a usage of the of t prime? Because we have t prime showing up here, and it's the application, and then t prime is also showing up in the body of the type. So does that count? Should it count? Anyone have a guess? There's two answers, so you have a 50-50 chance. What? No, okay, so we have some people saying, no, you shouldn't be allowed to do that. Does anyone think you should be allowed to do that?
What if the function just gives you back the thing that you have? Then you have to get up, right?
Yeah, the identity function is okay, because you get the argument and you use it up to return it as a value. Like the thing I'm worried more about is something like, let's say the body behaves a bit like the identity function. And this b is something that says something like, oh, I'm going to return you a value which is equal to your argument. So you can imagine, that, and that's actually pretty reasonable. So we might want this b to be something like this whole type to be something like, oh, if you give me an a, then I will give you back another y of type b, and I want this to be a here. And x is equal to y. So it's going to return a pair saying, if you give me an a, then I'll produce a new a, which is equal to the original one. And this is sort of at a conceptual level, this is a perfectly reasonable thing to do. Like, we are using this linearly. Like, I get one input in, and I produce exactly one output, and I tell you that the output happens to be equal to the input. That's okay, but the problem is that even though this sounds reasonable, nobody knows how to do it. So this is part of why I said that it's often worth taking a crack at a problem, like even if other people have failed, because sometimes you just need a new idea. And this is all really a situation where a new idea is necessary and no one has quite been able to produce one yet. Yes?
Do you have some summary of where trying to do that goes wrong using old ideas?
Let's see. So if you try to write down a semantics of types, it is extremely difficult to write down something that's not just complete nonsense. So it's not even at the level of, oh, there's like some subtle technical issue. It's how do you write down a definition that like isn't obvious rubbish? And this has been a big problem for a long time. And nobody has a good answer to this yet. There have been, I guess, 4 major attempts to combine linear types and dependent types. One was Frank Fenig and some of his students developed a system called linear LF about 10 or 15 years ago. And let's see, what are the others? Oh, yes. A second attempt is the system that I'm going to tell you about today. A third one is that Connor McBride has developed an alternate approach to the one I'm going to show you. And we argue about which approach is better on like sort of subtle and pedantic technical grounds. And Matthias Vakar, who is a PhD student who just finished up, he's also developed his own linear and dependent type system. And the fundamental idea that all four of these systems have is that we all said, that looks hard. Let's not do it. And like the exact manner in which we try not to think about this varies across all four systems, but really at the end of the day, that's the common theme. So we have a problem and we don't know how to solve it, so we don't. And this is actually why I started off by telling you about this adjoint logic system. So the thing is that, dependent types make perfect sense in a linearly typed, intuitionistically typed setting. So the generalization from simple types to dependent types involves quite a lot of bookkeeping, but but nowadays it is no longer a terribly difficult thing to do. And the generalization from a pure linear type system to a dependent linear type system is no one has a clue how to do it. And so the observation that Pierre and I made was that we don't need to do that. We've got this presentation of linear logic where it coexists with an intuitionistic system. So we can avoid the issue of what does a dependent linear function space mean by only making the intuitionistic fragment dependent. So at a very high level, what we are going to do is we are going to change the syntax of the intuitionistic fragment to be a dependent type system, and we're going to leave the linear system basically alone. So we're going to say we still have units, and the pair type is going to be turned into a dependent pair type, and the intuitionistic function space is going to be turned into a dependent function space. And now we actually have enough dependency to do the kinds of applications I was telling you about at the very beginning of the class. So I said, well, okay, we have like about 75% or 66% of the changes necessary to do all the applications. And so now we have dependency, and the restriction of this system is you may have dependent types, but types may only depend on intuitionistic terms. And so our goal is we're going to say, now that we have this notion of an intuitionistic dependent type system, then we can give types to things like these imperative programs in a fairly nice way. So what we can do is we're going to say, intuitionistically, we had this pointer type. Let's keep it. And I told you the other day that this is going to be one of the rare situations where dependent types makes things simpler. So because we have dependency on intuitionistic values, we no longer need to have this weird index on the pointer type. We just have a type of pointers, and it means all the passable addresses that are valid. And our capability type, yes, let me change this. Our capability type is going to be, a term that is going to be a linear type where we depend on an intuitionistic term, and we know that the contents are x. Okay. And I guess we'll still need the monadic type of linear computations. So basically, we'll take what you saw the other day, and now we're just going to make it all live in a dependently typed setting. And this works pretty well, and there's one more extension that we'll need to this system whose purpose will become apparent once we try to give dependent versions of all of the constants that we saw before. So let's start by seeing how things like dereferencing, pointer dereference work. And so let's say we want a read operation. Is this visible from the back? Okay, great. So now the idea behind a read operation is, actually let's do write. That'll have an even smaller type. So, and we might as well start with or even free. Let's start with free. And the idea behind free is we said, well, if you give me a pointer and the permission to access that particular location, then I will get rid of that for you. I'll deallocate that memory and you lose the permission. And so what we will do is we will say, if I have a pointer x, then I will have a computation which will take a capability and it will delete that memory for you. So you can read this as, give me a pointer, and now I have a computation that will take the permission to access that memory and surrender it to the runtime system. And this for all has been replaced with a pi, and we no longer need to index pointers by like the name of the pointer. And something similar will happen with new. So let's create an allocation operator. And what this will do is it will say, and now we're going to see why we'll need to extend the type system. We'll say what allocation does is it's something you can call as often as you like. And when you execute it, so we have the monadic type there saying this is going to be a type of computations, we want to get out a pointer and a capability. So we'll say, now. So does anyone have a suggestion of how I can write this? Let me pause there. So the idea is I want to put something here which says I get back a pointer and a capability accessing that piece of memory. What? Okay. And what should it say? Okay, x is a pointer. Uh-huh. That depends on x. Okay. Okay, yeah, let's return a unit. Okay, so this is like 99% correct. And the only thing wrong about this is that it's not in our grammar here. So what we have here is we're saying, oh, we want to return a pair consisting of an intuitionistic value And over here, we're saying, oh, and we want to return a linear value. And let's see, and this whole thing here needs to be linear because it's coming back from a computation. So you're absolutely correct about what should happen, and the only problem that we have is that we don't have this in our syntax. What we have is this f of x, and we have this tensor, and at present there's no way for a intuitionistic value to depend for a linear value to depend on an intuitionistic one. So in the syntax, before you extended it, the best we could have done is we would have had a computation which gives us a pointer, and we wouldn't have any way to say that this index is the same as that pointer. And the suggestion for what to write down is basically the correct extension to dependent types that you need. We said we're going to solve our problem by only permitting types to depend on intuitionistic values, and so we need to say when we have an intuitionistic value in the linear subsystem, we need a way to depend on it. Okay, and so what we're going to do is we're going to change this to you could use sigma, but in our paper we thought it was cuter to write f of x dot a. And so this is a pair type consisting of a intuitionistic value and a linear type that depends on that intuitionistic value. And the analogy we were thinking of is that exists was invented as a sort of backwards E, and we had an F in the original adjoint logic, so we thought, okay, we'll just write fx dot a. So if you wanted to write this in the syntax of our paper, we would have just written F instead of sigma. But that's just a choice of notation. Yes?
Would it be a correct term if you kind of wrap that whole the previous thing in an F and it's like a G around the capability right in the middle, or that does not mean the same thing?
Yeah, that wouldn't mean the same thing anymore. And the issue is that what G means is it means in an empty context, you have a linear term of this type. And let me quickly bring up the semantics from yesterday for what G means in the. Okay. Oh well. Fit width. Oh well. Here is the meaning of G. Yes. So the meaning of G. Yes. Oh, yes, of course. Let me highlight the meaning of G. Okay, let me highlight the meaning of G. Does that ruin the legibility, or? It does? Okay. Okay, so I'll just point at it then. Okay, so the meaning of G is I have a computation that makes sense in the empty heap. So this computation owns no heap. Perhaps executing it will allocate some memory, but right now it owns no heap. And so if down here we had said, oh, I'm going to wrap this whole thing in a G, then that return value couldn't own any heap. And the whole point of having a capability is that you own something. So that's why we needed to actually extend the linear language with like a kind of dependent pair type. Oh, whoops. So luckily, this kind of extension is a conservative one. So what we can do is we can encode. So what we want to do in this example is we have f of x, and right here I just deleted it and said, oh, I'm replacing it with this pair type. So what I want someone to do is see if they can think of how you can encode the old f of x using this pair. Yes. Yes, that's right. So Dustin's suggestion, which is the correct suggestion, is that we had this old f of x, which had no resources but had a value of type x. And so he said, well, let's just encode it as a pair of a value of type x and a unit, since that's sort of irrelevant and doesn't own any resources. And so, yeah, that encoding works perfectly well. And then we've sort of strictly extended the calculus, and with this encoding, it's pretty easy to show that any term in the simply typed system has a corresponding derivation in the dependently typed system. So we haven't lost anything with this kind of change. So let's see, what time is it now? 11:45. Okay, so I have enough time to like draw lots and lots of typing rules. So the one problem with dependent types, actually the biggest problem with dependent types, is that when you have them, you have a whole lot of well-formedness judgments that show up, and everything is mutually recursive, and this makes the whole progress of working with a dependently typed system substantially slower than if you're doing something with a simply typed system. And so this is a large part of the reason why, despite the fact that a large percentage of the programming languages community use proof assistance in programming languages based on dependent types, only a very small fraction of that community works on dependent types. It's literally, this is a huge amount of bookkeeping, and it really like wears you out. I want to sort of tell you all of the rules because, or at least many of the rules, because I think it's sort of important to see what the architecture of one of these systems is like, and hopefully I can inspire someone to think about how do we, how can we like improve I want to say human-computer interaction, but really what I mean is like the human-mathematics interaction. And so if you see what one of these systems is like I think possibly you'll get a feel for sort of how much work it is, and maybe someone in this room will have an idea of how to reduce that amount of work. So for a long time, so this has happened once before. So for a long time, proving the type safety of a programming language was a very serious effort. So you needed to think very hard about the semantics of a programming language. You would develop its typing rules, develop a denotational semantics for it, and an operational semantics for it, and then you would prove like some fairly intricate theorem to establish that well-typed programs don't go wrong. And in the mid-90s, Wright and Formalizing invented this technique called syntactic type safety. And they said, oh, we'll just prove if you can give an operational semantics and establish that there is a progress lemma which asserts that any well-typed term is either a value or will step, and every transition preserves types, then you've established type safety. No need to do anything more. And so they turned like this whole elaborate effort into proving two relatively easy lemmas. And that's why if you look at the decade before 1995 and the decade after, there's probably like 10 or 20 times as many papers on new type systems in the decade after as the decade before. And I think we are in need of a similar sort of idea to improve the efficiency of designing dependent type theories. But we don't have that, so I want to tell you about a dependent type system in dependent type theory in detail, so you can understand like sort of what the problems are. So in a dependent type system, what we call it dependent because the well-formedness of a type depends on the earlier bindings that you've declared. So the key thing is that, even forgetting about linear types for a moment, if you have a type pi x we might say, oh, if you give me two x's, we can return a sum type telling you whether they're equal or not. So this would be a decidability of equality. Not. Sorry about the parentheses proliferation, but I find it helps parse things. And so this is saying, oh, I have a function, and I have a binding of type x and another binding y of type x, and I'm returning a sum, so a coproduct telling you either it bears a proof that x is equal to y, or I have a proof that x equals y is a contradiction. And so now instead of having your Boolean blindness, you have like a proof-relevant Boolean here, which tells you this is equal, like this proposition holds or its negation does. And the key point here is that this thing right here is a type. And this type has lots of variables occurring in it. It has the variables x and y occurring in it. And this x and this y are bound by these quantifiers, these pi quantifiers. And so the point is that like the syntactic well-formedness of a type can no longer be given by some simple little context-free grammar. Whether a type is well-formed or not depends on which variables are in scope. So if I had changed, say, this y to a z, then this type is no longer well-formed. So what we have to do is we have to say, in addition to all these contexts, we have to introduce a bunch of new judgments to judge the well-formedness of everything, basically. So we have to say under what circumstances a context gamma well-formed, and whether x is a well-formed type, and then once we have whether a type is well-formed, we need to say, okay, does a term have a particular type? And let's see, we need another equality judgment. And that all of the judgments? I think, well, I haven't gotten to the linear ones yet. So I'll get to those on that whiteboard, I think. And the thing that makes this kind of this set of typing judgments difficult to work with is that every single one of these will depend on all of the others. So rather than I have like a collection of like independent type well-formedness judgments that like I can prove things about separately, everything is dependent on everything else in a huge mutually recursive tangle. And even establishing very basic syntactic properties is a lot of work. And then establishing properties that you think ought to be syntactic sometimes turn out to be like very complex semantic properties. Okay, so we want to have a whole bunch of judgments of this form. And what we're going to do is we're going to say, when is a context gamma well-formed? And so what we'll say is, okay, well, contexts are either empty or they'll tell you that a variable is in this context at a particular type. And the empty context, it's easy to tell that it's well-formed because it is. And if you have a context, let's see, how do I want to do this? Yeah. And if you have a context, how would we tell that a context gamma extended by a single binding is well formed? So I want to hear someone guess. Yes. What's your name? Are you, what? Andras, please tell me.
Gamma is a value from context.
Okay.
X is a value from type in gamma context.
Yes.
Additionally, you might want to say that X as a variable does not appear in gamma. Or is in the domain of gamma.
Okay. So yes. So I will accept two of your conditions. Your third condition is a good one, but I will not put it down. I'll tell you why in a moment. So Andras's suggestion was, in order to tell if a context with one extra hypothesis is well formed, what we need to do is we need to check whether the prefix is well formed. The prefix gamma is well formed, and then we check to see if X is a well formed type in the current context gamma, which we have just established is well formed. And you can see already that like the beginning of everything depending on everything else is now visible, because we've asserted that we need to assert that X is well formed, and we can only do that in this context gamma. And let's see. How am I going to do this? Okay. So let's do these three for the well-formedness of types. So next we'll say, okay, well maybe this won't be so terrible. Let's keep going, and you'll say, okay, let's judge when types are well-formed. So let's start with the unit type. When is the unit type well-formed? What? Always. So I hear a suggestion that we should write this. Does everyone like this, or does anyone have? Does anyone worry about it? Okay. I don't know who said it, but I heard someone. Well, why don't we check that the context is okay? Let's leave that in. So whether you check whether you put in a well-formedness check on the context or not is a design decision. Both decisions can work, and as long as you make all the choices coherently. Like what will change is the statements of dilemmas. So if you put in a well-formedness constraint, then your theorem will be of the form, if gamma asserts that X is a type, then gamma is a well-formed, and so on. And otherwise, you'll need to say something of the form, if gamma is a well-formed context and we have a derivation that gamma tells us that X has a type, then blah, blah, blah. So either choice can be made to work. You just have to make all the choices consistently, and this is difficult to get right. Like invariably what happens is you pick some things that you think are coherent, you try to prove something about the theory of the type system, and then you discover that like in 17 different places you made choice B instead of choice A. And in another 3 cases, what will happen is you'll discover that you need a premise which is, strictly speaking, redundant, but you can't prove that it's redundant until like you've done all the whole theory of the system. And so you have to keep it in, and then do all your proofs, and then once you've done all your proofs, you can prove that that premise was unnecessary. But I want you to see everything being dependent on everything else. So let's just make this make this go through. Okay, so let's do pi types, and then I'll skip sigma types because I don't want everyone to get too hungry. So how will we tell that a pi type is well formed? Okay, someone said let's make gamma okay, and then okay, X is a type, and then what's the last? Yes, so that will be fine. And let me put this in parentheses. Yes?
That gives me simplified to gamma with X and Y has type.
Oh, yes, I forgot to write Y type. Thank you, Charlie. So Charlie pointed out that we actually need to assert that well is well formed rather than type is well formed. Yes. So now I'm going to tell you like one of the reasons we keep making mistakes. So here, this gamma being this check on gamma being well formed is actually unnecessary because at the leaves of these type well formedness judgments, we'll always assert that gamma is well formed, and so here, if we do this consistently, then the fact that X has a type is a judgment that X is well typed in gamma. That will imply gamma is well formed. So you don't actually need that in this case. And if you're implementing a dependent type system, you want to do as few of these checks as possible. And when you're proving things about dependent type systems, you usually want as few premises as possible because the proofs get very, very large. So now we can now we're just going to talk about unit and pi types, and I'll say that's enough for now. And let's talk a bit about when a term is well typed. So let's do the unit type. So I want to say that a unit has the unit type. So is that plausible to everyone, or do you think I need more premises? Yes.
Can you say that gamma is well formed?
Yes. Dustin said let's check that gamma is well formed, and that is a fair thing to do. And now let's do lambda. Okay, and what should we do here? What do you think? Yeah, yes, you're right. It's actually right over here, and it's just in black rather than blue. And so what we're going to do is let's just leave those there, and that will give me enough room to put in like sort of the last two rules of term checking here. So we have units, we have functions and their application, and now let's talk about variables. So I want to say that x has a type. What do I need to check? So how do you find the type of a variable given a context? Okay, so you said belongs to the context. What should belong in the context? Okay, x has type x in gamma. Okay, any other conditions? Okay, Charlie suggested well-formedness again, and yes, let's put that in. So sort of the invariant we're trying to maintain is that if one of these judgments holds, then we'll also want to conclude that the context is well-formed. So we'll only be able to give a typing derivation in the circumstance that the context and the output type is well-formed. So this is sometimes called a regularity lemma. Ah, yes, I did forget one of these judgments. Not A and B, X and Y. Okay, so I will in the interest of time, and because I forgot to set things up at the beginning, you can see up here that we have two judgments, one asserting that a type is well-formed and one asserting that a term is well-typed. And similarly, we want to have two equality judgments saying that x is equal to y as a type and E1 is equal to E2 as a term. And so there's a lot of names for these. These are sometimes called conversion, sometimes called definitional equality, sometimes called judgmental equality. And the one thing this is not is it's not propositional equality. So this is, so the purpose of this is to say, well, if E has the type X and X is equal to Y as a type, then E has the type Y. And this equality judgment is what we're going to check on the next whiteboard. Okay. Yes, I want to bring this down. Okay. So we've got about, I would say, like at least 40% of the typing rules written. And you like already you should be thinking, wow, this is a lot of rules, because this is basically a type system that has units and functions. And we already have exceeded what you would need to write in the simply typed case by, I guess, a factor of 2 already, and we're just getting started. So this is really kind of peculiar because dependent type systems are like very natural to work with, and it's kind of surprising just how many conditions you have to check. So like they line up very, I find they line up very well with natural mathematical reasoning, but when you formalize it, it's like, okay, so natural mathematical reasoning is a lot more complicated than I thought it was. So what we want to do is we want to judge when two types are equal. And this is one of these things where in this particular case, it won't be too bad. But you're going to see everything is dependent on everything is mutually recursive with everything else phenomena show up. So what we want to do is we want to just give some rules for when different types are equal to one another. I want to add one more type here. Let's stick in, I'll put in like some atomic type. Let me make up a type. Let's put in equality as a type. And what I want to emphasize is, I apologize, but there's no really good notation here. So I'm writing E1 is equal to E2 to mean this is a type saying that E1 and E2 are equal. And I'm writing the triple equals to say that X is definitionally equal to Y. And this difference between a definitional equality and a propositional equality is a fairly important one, but I'm not going to get into it. For the moment, I'm just going to apologize that there's like some notation that looks almost exactly like some other notation. And so let me quickly come back here so we can say what it means for an equality to be well formed. So we want to say that E1 equals E2 at type X is a well-formed type just when X is a type and both E1 and E2 have that type. Is that visible on the video, or should I make it bigger? Okay, it's still visible. Okay. Okay. And I'm putting that type in because equality is important in logic, and also because it'll give you the full experience of everything depending on everything else. And so the point is that, like, for the most part, when two types are equal, are judgmentally equal, is something that you can manage just by like following the structure of types. So we can say, and I'll give you some of the easy cases to get you started. We can say that, well, the unit type is definitionally equal to the unit type. Let me digress for a moment. So this whole business of having a separate definitional or judgmental equality and a separate propositional equality it's often one of the things people find hardest to understand about dependent types. And the place that it comes from is that sometimes there are equalities that require proof. Like, for instance, if you have an implementation of quicksort and an implementation of merge sort, they compute the same function, at least if you did it without bugs. But the fact that they compute the same function is not obvious. You have to do a proof. But in other cases, you shouldn't need to do a proof. So the logician Jean-Yves Girard once remarked that, like, an equality is only interesting when it's false. And what he meant by that was that if you write down something like 2 + 2 is equal to 4, well, that's, if you look at it, obviously that's not true. There's a 4 right here, and there's 3 ASCII characters over here. So, you know, it's just not true. And so the interesting thing about equality is that, like, we're somehow asserting that that these symbols are equivalent to one another for some kind of reason, and that's why he said inequality is interesting only when it's false, because, like, the only really obvious equalities are the ones where you have the same symbol standing for the same symbol, and if in all other cases there's, like, some sort of more philosophically interesting reason why we're making this assertion. And the introduction of judgmental versus definitional equality is sometimes justified in terms of the logician Frege's distinction between sense and reference. And so Frege was also sort of puzzled by this question of, like, what does it mean for things to be equal? And he introduced this famous example of the distinction between sense and reference. And he said, so in English so in mathematics we have this idea that if two things are equal, we can always substitute one for the other, and the meaning doesn't change. So if we know 2 + 2 is equal to 4, then in any mathematical expression where we write 2 + 2, it's just as valid to write 4, because they mean the same thing, and the meaning of mathematical propositions, you know, shouldn't depend on, like, you know, how which name for a mathematical object you used. But on the other hand, this principle is actually false in English. So, for instance, in English, there's the morning star and the evening star, and these are visible at dawn and dusk, and they're both the planet Venus. So the meaning of the denotation of morning star is the planet Venus, and the meaning of evening star is the planet is also the planet Venus. So it's a little bit puzzling about human use of language that if you say the morning star is the evening star, you've learned something, and yet, like we feel like this is new information, and yet the reference or denotation of both of these terms is the same thing. And so if we believed, oh, equality means you can substitute equals for equals, saying the morning star is the morning star doesn't tell you anything, or Venus is Venus doesn't tell you anything. That's just a triviality. And so the idea that Frege had was, you know, we have so terms have a notion of sense, which is, you know, which is like sort of a weaker notion of equivalence than their reference, which is their true denotation or meaning. And so he said, well, the solution to this problem is that there's two notions of meaning in play. There's the reference of a term, which is the thing it actually refers to, and then there's the sense, which sort of, to some extent, includes some of our understanding of it, but not like completely. And so in type theory, we introduce this notion of judgmental equality to talk about the sense of two terms. And we introduce the notion of equality to talk about their equivalence under reference. And so if you have the proper function definition for plus visible, then Agda and Idris are perfectly happy to evaluate 2 + 2 and find that it's 4 and tell you that 4 is equal to 4 with no need of proof. But on the other hand, if I tried to say, oh, is quicksort equal to merge sort, then Agda will complain and say, no, I don't know this. Like, this isn't obvious. They don't have the same sense. And then you'll need to sit down and do an inductive proof to prove that quicksort is propositionally equal to merge sort. So that's a bit of a digression, but like I think it's an important one because people often get confused about why are these two separate notions of equality running around in type theory. And the short answer is basically because we use language in different ways. And in order to make our programming language sort of match mathematical usage a little bit better, we introduce this distinction back into type theory. And so what we do with this notion of equivalence is we say, I don't have that much time, so I'll go a little bit quickly. What we're going to do is we're going to say two types have the same sense when it's sort of obvious that they're the same. So for unit types, it's obvious that they're the same. And I'm going to say, when is it obvious that two pi types are the same? Oh, I don't want to use it. And the sort of the easy answer is, well, if you have two function types, they're obviously the same when the domains are obviously the same and the codomains are obviously the same. So we'll say a type X is a type. And now you're going to see the bit that causes a lot of problems in the meta theory of dependent types. So when is y obviously the same as y prime? Any suggestions? Yes. Oh, yes. You're right. What we should do: x is equivalent to x prime. And then what should we write? Uh-huh. Yes. So this is correct. So this is correct. And when you do the theory, it's also very troublesome. Because we've asserted x is equal to x prime. And here in the body, we're saying, OK, now that we know that x and x prime are obviously the same, we're going to assume that the variable x has the type big X and show that y is equal to y prime. And the thing that's tricky is that this y prime was defined in the context of a variable of shape x prime. And we're saying we're going to put it in the context of shape x. And so we wrote x here. We could have written x prime, and then we would have had exactly the opposite issue, that this y was defined in the context of an x. And it doesn't look like a big deal, but when you go and do proofs, like a lot of ingenuity is required to avoid having to or in order to cope with the fact that we're replacing this x with an x prime. So I said, oh yes, judgmental equality is two things are obviously the same, and and I guess the thing is, it's not obvious that they're obviously the same. And let's see, what will we do? Okay, and so now we can finally say when are two equality types, E1 equals E2 at type X, obviously the same. And the reason I put in equality will become visible now, because as before, this is just sort of fully structural. This doesn't happen in all dependent type systems. So if we had the ability to compute types the way you do in Idris, then this type equivalence would be more than a congruence. But then there would be even more rules. So first, we're going to check that x is equivalent to x prime. And then we'll check that E1 is judgmentally equal to E1 prime, and E2 is judgmentally equal to E2 prime. And again, the same issue arises that like E1 prime and E2 prime were originally checked at X prime, and now we're checking them at E1 prime. So there will be more bookkeeping than you would like. Oh yes, also need this. So once we have all of this, look, here's yet another bit of mutual recursion. Yes.
So in this case, it's plus 38. Why wouldn't just check at one? Oh, never.
Okay. Yeah. So the reason you don't think you need to check is we're saying we have this typing rule right here, which says that if E has the type X and X is definitionally equal to Y, then E also has the type Y. And in this premise, we establish that X is equivalent to X prime. And so it's safe to say E1 prime and E2 prime have the type X. The only problem is that, like, this makes intuitive sense, but keeping track of where all these equality coercions go and making sure that, if you're doing an inductive proof, that you haven't stuck in extra equality coercions that made your term too big. That's sort of the thing you have to watch out for. And finally, and I'm going to try to be a little bit quick, so I'll gloss lightly over this, over the term equality. We will have a term equality as well. And the term equality is where all of the computation goes. So I'll do the pi type as a representative example. So generally, there's going to be where you're going to put the beta rule and the eta rule for typing into the judgmental equality, and then you'll lift it up to like have the congruence rules and the reflexivity and symmetry and transitivity. So what we'll do is we'll have some axioms saying, oh yes, lambda x dot e prime is equivalent to e prime for x in E at the type e prime for x in Y when E is a function and E prime has the type x, and then the application is well typed out here. So this will be the beta rule for pi beta. And there will also be a corresponding eta rule, which says that if E has the type pi x dot y, then E is judgmentally equal to lambda x ex. And then you're going to have rules saying that, congruence rules saying that E1, E2 is equal to E1 prime, E2 prime, when E1 equals E1 prime. Let me do one congruence rule. So you'll have rules of the form E1, E2, and I'm just going to leave off the type annotation here because I'm running out of room on the board. So we're just saying that that a equivalence relation, that the judgmental equality needs to be a congruence, and it'll also be symmetric, reflexive, and transitive. And then it will also throw in the beta and eta rules for each of the types. Yes.
So I think that most of the stuff we've done with types requires that certain types be derivable, but not necessarily unique. So is there any place that we would have problems if when we use, say, x prime, but we're using an x because it's equal, if we just stuck in x of type x and x of type x?
when you're programming in a dependent type system, this never causes you a problem. Like the whole point of having a rule like this is that, you know, if two things are sort of judgmentally equal, they are the same, and you never need to think about the difference. And you know, and like basically all implementations of dependent type systems satisfy this property, because if they didn't, then the systems would be badly broken and unsound. So from the user side, this all works well. You don't need to think about it. It's when you are proving things about the dependent type system that this causes a problem. So yeah, so so from the perspective of a user, if you have an x and you have a y, and you know it's equal to a y, then it's interchangeable with treating E as having type x and having type y they're indistinguishable. But when you're doing, say, a proof by induction on derivations, you may want to say, oh, I have an x, I need a y, and I'll use I'll use this conversion rule to replace one with the other. But depending on the kind of proof that you're doing, if you're not careful, like applying a rule can make a derivation bigger, and you might not have like a proper inductive proof if you're not careful. So this kind of the careful bookkeeping is like one of the hassles that you have to be aware of. But it's a hassle that somebody needs to take care of, but they only need to take care of it once. So once the developer of the type theory has finished their proofs, then no one else needs to worry about that again. So like the kind of research question is that frequently we want to build lots of new dependent type theories, and unfortunately this is checking these kinds of basic syntactic properties like weakening and substitution are often very intricate. And you know, it seems like it's much more intricate than it should be, because pretty much once you've worked with the dependent types for a few months, you can pretty much just write down rules and tell that substitution ought to hold, and you'll be right. Like sometimes you might make mistakes with oh, do I need a conversion here or not? But they're always very trivial and shallow. And so there's like clearly some principle that people are using that we haven't like properly articulated yet. And so if somehow we could come up with that, then you know the process of producing new dependent type systems could be made a lot simpler, I think. But no one knows how to do that yet. Yes.
Can you try to do intrinsic definitions of type theory in order to make substitutions and renaming and kind of basic syntactic properties to go away?
So it depends on what you mean by intrinsic.
For example, high inductive.
So you mean doing the theory of dependent types in a dependent type system?
Yeah.
There is a lot of active research on that, and it's a research topic because it's a much harder way of doing things. The basic problem is that what we're writing down here are a bunch of big derivation trees, and we're working with them. And if you try to do a sort of theory of dependent types and dependent types, the data types you naturally write down will end up being dependent on the specific derivation of judgmental equality, and this ruins everything. Like the point of having a judgmental equality is you don't care which proof of judgmental equality you have; they're just equal. And you know, in a naive proof in a dependent type theory, like your definitions will be dependent on on the choice of derivation, and now there's like a whole bunch of coherence proofs you have to do, which are like hairy and horrible.
Yes, but we can just like truncate all the.
So truncation, like if you forget about like the fancy homotopy type theory stuff for a second, what you're doing is you're saying, oh, well, I have this thing, and now I'm going to quotient by the derivation of definitional equality, and what you have now done is it's an improvement in that like the place where you have to check these coherence conditions is reduced to one spot, but you still have to check them all. So it's an improvement, but not like a perfect improvement. Yes?
Just a silly practical question. You talked about the difficulty of all these proofs, and your Popple paper is 14 pages long or something.
Yeah.
What do you do with all these proofs?
So the thing is that like I want to just make a distinction here. So the proofs are generally not hard; they're long, and this is really the problem. So if a proof were hard, that's okay because that means you had to think. But if the proof is long, then that's sort of like a waste of a human being's life. Like frequently, like establishing these properties is like it feels really mechanical when you're doing it, and you're like, there's no ideas here. There's not going to be any ideas for the next 50 pages of this proof.
So there's no real need to publish it anymore.
Well, you have to do it because you'll get it wrong unless you do the proof. But you wish you didn't have to. So sort of the point of all this is that the move from simple types to dependent types is very natural from the point of view of like a language designer or a user. It's just because all of these judgments are dependent on one another, like the complexity. So the complexity in the sense of bookkeeping gets a lot higher, and this is a problem because nobody wants to spend their time doing like if I wanted to do like sort of tedious bureaucratic things, I could do my taxes, and sort of the open research question is how do we build dependent type systems more efficiently in terms of human labor? Yes.
So I have a question. In the corner, you say if x and y they are judgmentally equal.
Yes.
Then x and y they are a type.
Yeah.
But in the syntax of types, if x and y they are judgmentally equal, they are not. There is no syntax of types for that.
So there's no
Yeah.
this one.
Yeah.
So that shows up right over here.
Yeah. Y x 3 bar y is a type.
Oh, okay. So the way you should read this is x and y are judgmentally equal, considered as types. And here you're saying E1 and E2 are the same at the type x. And so like the point is that like there's like two full whiteboards of rules stuffed everywhere, and we haven't even gotten all of the rules yet. And this is basically a dependent version of the simply typed lambda calculus. So there was sort of a big jump in the number of rules, and yet the sort of conceptual distance isn't that great. And if I had 5 more lectures, I would spend some of them going through these proofs bit by bit, because I would say at least the first 2 times it's good to do, because one time it's sort of good just to learn how all the pieces fit together, and then do it a couple of more times so you can get a feel for what's the common structure between different type systems, and then after that you really start questioning your life choices. So like personally, I have like this big research agenda involving dependent types, and it is currently stalled on my willingness to do more of these type safety proofs, well, type normalization proofs. So I have a very good master's student who's done one of these proofs, and like, you know, I just need another one to do the next proof, and then we'll have a paper. And the thing is, though, that like I don't think this is like really a scalable process, because you know, the thing is with a graduate student, you want to give them the interesting problems, not the boring ones. So anyway, the point is that, you know, we can set this kind of thing up, and then in order to get back to linear types, it's actually like a fairly straightforward process, because what we're going to do is we're going to add one more judgment saying that A is a linear type, one more judgment saying that T has the type A, and we'll add like another parallel set of judgments here, saying that A has a linear type, T has the type A, T1 and T2 are judgmentally equal, and A and B are judgmentally equal as types. And they'll all follow this pattern, and they'll be simpler because there's no further dependencies in the linear fragment. And then when you put that all together, you'll actually get a language that turns out to be, I find, a very nice one for doing dependently typed programming in. Like, there'll still be, like, you know, a lot of engineering you have to do once you have the theory for things supporting things like type inference and tactics and things like that. But I think it makes a very good kernel type theory. I want to let you all eat lunch. So if any of you are still around after the Amal's lecture this afternoon, I will tell you about my favorite fixed point theorems and how you can use them to define logical relations on dependent type systems. Okay, thank you.